training organized by University of Ljubljana. So today we'll be talking about industrial automation, and we'll have interesting lectures from imaging systems to using PLCs and programming of those, as well as a lecture on IoT technologies and some things related to the newest trends and newest technologies such as blockchain. So for the start of the session, if I can just ask you to turn on your cameras just to say hello and to make a nice screenshot for the purposes of the reporting for the project, that would be really nice. So yeah, if you can just turn your camera on for a few minutes, just here at the start. Hopefully you can hear me. Is the sound okay? I can only see Drago, so can everybody else maybe, hello, okay, can everybody else maybe just, yeah, show your camera just to say hello.
Your sound is okay.
Okay, thank you. Okay, anyway, our first speaker of the day is Drago Brăciun. We're colleagues from actually the same laboratory, which is the Lab for Mechatronics, Production Systems and Automation. And Drago is an experienced professor and experienced researcher, well known for his work with the industry. So working on real life problems, not just the academic ones, mostly related to imaging systems in general, everything from building custom 3D scanners to using the newest methods of artificial intelligence in image processing these days. So with this short introduction, Drago, please, the floor is yours.
Okay, thank you very much, Rok. Hello, everybody. I hope you can hear me quite well. Maybe I should share my screen for the beginning. That's one nice picture for background. Okay, maybe I should introduce myself at the beginning. So as Rok already said before, I'm a researcher and assistant professor here at Faculty of Mechanical Engineering. So my interest is primarily in application of advanced vision systems in monitoring, diagnostics and prognostics of industrial systems and processes. So in practice, this includes some 3D body shape measurement, visual inspection of parts, then CNC and robotic localization systems. We cooperate a lot with also with guys from welding laboratory, where we develop together wire arc additive manufacturing methods, and here we use vision systems for monitoring the process and all kind of effects around this. I also had many industrial projects, from measuring large hot work pieces at open die forges, if I only expose few of them. Then localization system for CNC milling of large composites parts for wind turbines. Then there was some interesting project for automotive industry for visual inspection of automotive parts. So we built an automated work cell which inspect part each. So each new part is inspected within 5 seconds. And so this work cell included 2 industrial robots, 14 cameras, 4 laser scanners, a lot of computers, and it was really big stuff. Now our research is directed in direction of deep learning and those methods which are today quite state-of-the-art in image processing. Yeah, that's about me. I hope you hear me well. If there is some problem, just tell me. Now I will switch to topic that we have today. Just a second. Okay. Can you see my slides?
Yeah, yes, everything great.
Okay. Okay, today I will present you subject called imaging systems. This subject, I have lectured on this subject, is in the first cycle professional study program in mechanical engineering here. So this is quite practical oriented lecture for guys who have 3.5 years of study here in faculty and then go to our industry to work with automation and the processes and everything in industry. So this lecture is for mechatronics direction. We have 4 different directions within this study program. I hope you already heard something about this. So within mechatronics, I think those guys must be in this mechatronics direction because we have also a lot of programming working with electronics, equipment, optics, and so on. So you must have some appropriate background for this. Okay, we have 30 hours of lectures. That means that we meet 50 times with students for an hour and a half. And we also have 30 hours of laboratory exercises in this subject. So the main objective of this lecture, this subject is so that students understand how to use machine vision in automation and in quality inspection, product inspection, and so on. So to get some basic knowledge of main building blocks that form these machine vision systems, so that they know how to develop such vision system, how to derive specifications, how to calculate required components, how to select components, how to assemble everything, and how to also program. Regarding programming, here we could complicate from very simple to very demanding programming. So in this lecture is actually our main goal to teach these students to get some basic knowledge of image processing. So we don't go deep in some C++ algorithms and processing and so on. We more stick on some high-level software packages that already have pre-prepared some functions, and they only assemble building blocks. In this level, in this practical level, it is important for them to understand let's say if we start from some data formats to some logic, some pipeline, some functions, sequence of functions, how to use some software tools to derive something from images, and so on. We also put big emphasis on some general open source equipment as software. I will explain this later through the presentation of the lecture. Okay. Few words about learning and teaching methods. Okay. as we said, we have classroom lectures of theoretical and practical examples. We have laboratory work with some equipment. And at the end, each student do its own small project seminar where he gets some specific task and then develop imaging system for this task and program something and present results and write some report. Now I will go through the lectures. So as I said before, we have 15 lectures. We meet 15 times, but usually we left one lecture so that we are more flexible. So actually we have 14 topics. And now I will go through the topics and present you all these topics. So each lecture should start with some big picture. So, and here we also start with big picture so that we try to give students a general idea why we use some machine vision, some cameras, optics, and so on in automation, in quality inspection, what is motivation for this, how this looks in practice, and so on. In that view, we also show them some practical examples from, let's say, from my projects in industry. We show them complete story from the idea, from the needs of company, what were need, what were problem, was problem in some quality and there was need for inspecting quality, or was problem with some efficiency or process control or whatever. Then we show students how we approach designing this optical system, what were some boundary conditions, some space limitations, some environment effects, some environmental disturbances, like, let's say, like sun, like this sun strips on my face now. So we also have all kinds of problems in industry, starting from lights to dust, pollution, whatever, vibrations, and so on. And we try to show them big picture in the beginning. Then we go and explain them some general structure of the imaging system. That means that we try to explain them that we usually have three main components in those imaging systems. The first is optical part, where output of this optical part is image. Then we have image acquisition. So here we use camera. And at the end, we have image processing, where we extract something out of image. And we really put big effort in the first part, in this optical part, where we have illumination. We should select proper lights, illumination, and so on, to illuminate the object. And here, in this illumination of the object, we have all kinds of optical effects that we must utilize them to get image at the end, because then we have only lens that create image of the object. So we have to illuminate the object so that the things that is important for us is visible on the image and nothing more. in this scenario, it is very important to explain them also how shape and some surface properties of the workpiece, from color, reflectivity, and so on, can work for us or against us. And then here we go for different lightening effects from and so on. And at the end, we also in this part we also say a few words about lenses and optics. So to acquire image of good quality, so that it is only visible what is of your interest and nothing more. This is especially important then in the third phase, where we process images. If image contains only object of interest, and there is no some background noise, some other features in the background, image processing is very simple and could be done really simple without any special knowledge. But if we do not succeed to get good image, then image processing could be unreliable or even mission impossible. We could implement, well, I don't know, maybe deep learning, some neural networks, whatever, but still system will be unreliable. We will need very demanding equipment and so on. So here in this lecture, I really want to explain them that if we acquire image where only object of interest is visible, then we can have a low performance computer, like Raspberry Pi or something like this, or if I exaggerate, or Jetson Nano or some small PC. And we can use very simple image processing functions, which works very fast and very robust, and the system performs very well. But if the first part is not solved good, then this could be mission impossible. So, and I think this is the most important thing for anyone who develop imaging systems, to be aware of this fact. So this is first lecture, and in next the following lectures we go through these basic building blocks of such imaging systems. So first we start with object illumination and all these lightening effects that cause that we achieve good picture without some background noise and so on. Then we go to the camera selection, then we calculate optics and measuring properties of the system. At the end, we go to the image processing, and then we have few lectures that are dedicated to specific use cases of the imaging systems. The use cases that they can easily meet in practice, or they will definitively meet in practice, and sooner or later we'll work with them. Okay, so the second lecture, as I told, is about illumination and lightening effects. This is the most important thing. So here about illumination, we always have three objects of interest. First is our object that we observed and the environment of this object. If this object is, let's say, on a conveyor belt or some holder or whatever, this object have some color, some surface properties, maybe this is reflective or not, so on. So this is one important consideration of the story. And then we have two additional. One is light, which light we will select to illuminate this scene. And now the question is where to put light with respect to the object. So we can put light in the same position as camera, or on the other side, or perpendicular, or at angle. With this orientation, different configurations of camera, light, and object, we achieve different effects. And those effects then are useful in some particular situation. Let's say if we would need to measure, let's say, to check some color or to check some text on some box or bottle, then definitively illumination in axis where camera and light are in the same axis with respect to the object is used. Let's say if we would use, if we will have, let's say, application where we will check dimensions, then maybe is the most favorable configuration where the light is on the other side of the object. So this is so-called shadow photography, where our object is actually dark on the image, everything around is bright, and we only accurately see the border of the object. And if this configuration is quite successful, the image processing is very easy at the end. Then if we need to check some surface features, let's say a roughness or some surface scratches or indents small or some other irregularities, then illumination which is perpendicularly positioned to the camera is important. And if we wish to measure 3D shape of the object, we have stereo vision or laser triangulation or coded projected projection of coded patterns, then we use illumination and angle. This is so-called triangulation principle we utilize. So here we really make big fuss about these illuminations and the effects and so on. And we also then go through different designs of these lights from different, we make some review of different manufacturers, what they offer and so on. Okay, that's about illumination. Then in lecture, we go to the camera and image acquisition. We explain student what is the main thing in the camera is image detector. This complete story about image detector, image acquisition, so pixels, number of pixels, bit depth, color acquisition, what is triggering, what is shutter, what is exposure. We go through all these parameters. Then we show them also different designs of cameras, starting from industrial cameras, which are made in some robust housings. We discuss digital communications, from gigabit communication to whatever. How we connect lenses, how we install camera to some fixture, what can be possible problems in industry. Let's say vibrations. More for a joke, I can tell you that in one company, this camera was, I have few cameras installed on some frame, and the robotic arm was also installed on the same frame, some support. And this motion of robotic arm is very periodic, and it was those arms make some very cyclic vibrations that traverse through this frame to the cameras. And the result of this was that the lenses start unscrewing from the camera body. And let's say after a week of operation, these lenses fell down from the camera. It was like there is a ghost that is doing something with our camera. It was really weird. And I'm trying to show and explain students all those scenarios that could attack them in practice. We also go through, we don't stick only to the industrial cameras, we also go to some embedded systems. On this lecture later on, we use Raspberry Pi. I hope you know this is a small computer with ARM Cortex processor, and we can connect this small embedded camera or some USB camera to this platform. It is not high performance platform, but it's quite good for a lot of tasks, and it's cheap, so we have this for our students, and then they play with this equipment. We also discuss a little bit more high performance platforms like NVIDIA platforms and so on, but we don't work with them because this already demands more time and more dedication, understanding of programming and everything. So this is more for seminars or for diploma or master thesis, if any one of those wish to work on this topic further on. So much about cameras. Okay, maybe worth. So in this lecture, they understand different types of cameras, what the key parameters, and how to select camera based on required resolution, color, depth, speed, and so on. So at this point, they already know camera and lightening. So we can then go to the lenses, because you can select lens after you already knew what type of camera you will have, because detector in the camera, physical dimensions of the detector in camera, and size of the field that you wish to observe, object size and the area around the object, actually then specify these border conditions based on which you then calculate and select required lens. Because you can have same camera and you can observe object from close distance, let's say 20, 30 centimeters, maybe half meter, or if there is a very demanding environment, let's say that you observe welding, melted pool, where you have extreme heat, smoke, speckles, and so on. You cannot observe this from a close, because sooner or later this camera will be damaged. So you have to observe it from far distance, let's say maybe from meter, and then the story is same. You have the same camera, same object, measuring size of the measuring field, and then you calculate the required lens, which will make image of this area of interest on the detector. And here we go through the basic math. We assume that each lens is a thin lens, So we don't in this level, because this is professional level, we don't go to some ray tracing through the lenses and so on. This is too complicated. Actually, it's not complicated if it is presented properly, but we don't have time. So here we primarily stick to the thin lens equation, because each lens, even with several lenses in combination, can be at the end assumed as one thin lens, and this is enough to calculate the required focal length and everything around this. Then we also show them some data sheets from the manufacturers. What is some key parameters around such lens, how to select lens starting from optical performances of the lens to the mechanical properties, how to connect this lens to the camera, how to adjust sharpness, iris, and everything around this. Okay, so much about lenses. Okay, at this point, we assume that we have the illuminated object, we have illuminated scene, we already have lens that create image detector inside the camera, we know everything about camera, and we have already image that camera acquires. So we continue this lecture with the story how the image is then grabbed, how we connect to the camera driver, how we grab this image, how we store this image into the memory of computer, how the image is represented in the memory, how we access it. So we also mention pointers and so on. Then we go through basic, through different software packages and discuss what they offer us and what is the level of required background to use these software packages. Let's say, okay, Super OpenCV is almost standard today for image processing, is free there. But if you wish to use OpenCV, you should know something about programming. So, and here we have different, again, we have different levels of difficulty. So we can start from programming OpenCV in Python, and actually we will have this through also through all laboratory exercises, because we will work with Raspberry Pi, and the main programming language will be Python, and then we will import OpenCV, so install OpenCV, import OpenCV, and then start camera from the OpenCV, grab image, and go through complete pipeline. So we dedicate image 3 lectures to the image processing, because this is quite a demanding topic, and we have to dedicate a little bit more time to this topic. So first, when after the students know how to grab the image, how the image is stored in memory, how to save, how to view image on the computer screen, then we discuss some pipeline from starting from image grabbing to some analysis like this one here, and then we discuss functions on high level, what to do with image to get something out, and then And we demonstrate this in few different scenarios. Let's say here for an example, I show scenario when we grab, let's say, when we have some different colored objects on a conveyor belt, and let's say that we have to determine exact location of this, let's say, green circular object. Let's say we discuss how should pipeline look. Let's say that we convert this image to the grayscale, then perform some thresholding, how to derive to the some binary image, black and white image, what are blobs, how to calculate some areal properties, some area, center of the gravity, and so on, of these blobs, and so on. In this manner, we go through different tasks and scenarios, and also show them how this programming will look in Python, as well as in C++, but we don't work with this on laboratory exercises. I only show them on lectures because C++ is already a little bit more demanding, and you need proper background. We don't want to complicate too much at this level. Yeah. So to conclude, we also go through different different categories of image processing functions. So let's say we divided them into the point operations, where we do something on each pixel. Let's say color modification or thresholding or adding, subtracting, averaging, multiplying, division. All these operations are performed on a pixel level. Then we discuss function, a little bit high level functions for object detections. Let's say some blob search, some geometric properties, some transformations, rotation, translation, scaling, and so on. And at the end, we discuss local operations. Those operations work in some surrounding of a specific point where we are. So primarily, we discuss here convolution. And we describe what is convolution, and then what kind of effects we achieve with different convolution kernels, from filtering to edge detection to feature recognition and so on. So this convolution is quite important. Also later on, we mention also some of these networks, convolutional networks we only mention, and this is state of the art today, so it's important for them to hear this big picture and everything around this. Yeah, so much about image processing. I will not go more in detail because here we could discuss really for a long time. Maybe we can later on, if there is a question, maybe discuss something. Okay, we can, until now, they learn about complete pipeline from starting from object illumination to image processing and to extract something for the image. So at the end, it is very important calibration. So we need calibration whenever we need to perform accurate measurements. So when we measure dimensions, or when we have to undistort lens distortion. So especially if we work with small cameras, then we usually have a lot of radial distortion, and then we have to correct this distortion. Just a second, I have to close the door. Sorry for this delay. So for this calibration, we actually here describe them how to use calibration bodies in form of some plates with coded patterns. This could be chessboard or some circles or whatever. What is the point of these calibration bodies? How to how to acquire images of this calibration body, how to process them, how to extract the data out of this, and then how to perform calibration. Here we demonstrate everything by using camera calibration toolbox for MATLAB. It's freeware toolbox on the internet. Peter Cork developed it, and students then use this software to calculate, to do this calibration, and they must understand all parameters related to this calibration, starting from distortion parameters to center of the image, to the focal length, and everything around this. After that, we also discuss algorithms for undistorting images based on those parameters. So at calibration, we determine some parameters of some distortion model, and then we turn this around. So we turn around this distortion model to undistorted images with these parameters, and they should know how to do this. Then we also at this point touch also the point how to calculate 3D coordinates in space. So if we know distance of camera from the object, and if we calibrated camera, then we are able to calculate accurately the positions in space if we know distance of the object from the camera. So here we go to the normalization to put into the same denominator inside of the camera and outside, and we go around this map and through some examples around this. Okay, so much about calibration. Then we go, let's say that until now, students are familiar with all building blocks of the imaging system. Now we go to some use cases that are most often encountered in practice. The first such use case is actually inspection of dimensions or some surface features, so something related to the quality of the inspection of the part. And we start this with a presentation of case study. We go into some case study. Okay, this one from case study from practice. Then we go to the development of the measuring specifications. So where to put camera, how to play with this setup to figure out proper position of the equipment, how to calculate required components, how to model everything, and so on. So complete engineering approach to the design of such system. Like you can see here in this image. Then for this use case, let's say we take some sample images from the practice that were acquired in practice with a real system, and then we analyze what the basic image processing functions required to calculate something out of the image. Let's say, like in this case, that we would have task to check this ring. So what is the pipeline, what to do with the image first, and then how to extract this ring, how to detect, let's say, inner edge, outer edge, how to, I don't know, calculate diameter, how to check if it is deformed, or something like this. So we go through the sequence of functions, and we test this with the simulation. Okay, we already have images. We simulate this in some high-level software, let's say like RoboRealm. This is software where we only assemble a pipeline. We only click on functions and we immediately see the result of some function, what this function does with the image, what is the current output, and so on. So it is quite straightforward demonstration of functionality and of this all those functions. Then we draw diagram how software for image processing should look like, starting from camera control, initialization of the camera at the beginning, frame grabber, so acquisition of images, where to put this code for image processing, how to control behavior of the program, where to visualize some results, and where to save if required, how to maybe switch some external signals. Let's say that our measuring system should give some signal if the part is good or not, or something like this. Then we discuss how the calibration could be carried out in practice, and so on. So this is one complete big picture of the one use case and all variants around it. Then the second use case is related to the 3D shape measurement. This is more and more often used in practice for all kinds of tasks, starting from bin picking to geometry inspection to localization problems, and so on. So here, first we describe how we actually can acquire 3D shape. So starting with triangulation principle, and then we go through different measuring principles, starting from laser triangulation to fringe projection, stereo vision. So in this lecture, we don't have time to go into detail, let's say, how this stereo vision or some scanner with coded projectors works, but more what are the algorithms. We don't have time for this, but we describe the principle of operation, so the big idea, how this works, what are the key parameters, and what is the output, and how to use this equipment. We discuss some challenges regarding this, all the 3D measurements, let's say especially regarding calibration of those systems, how to be sure that measurements are accurate. And then we go to the representation of 3D shape. Here primarily we stick to the point cloud, but we show also them that we can show this 3D measurement in different ways. So, okay, one way is with point cloud. This is where each point have 3 coordinates in space and color. This could be grayscale or RGB. So at least 6 different data for each point. And then we have maybe a lot of points, 100,000 million of points to show to represent object. However, we could also show this 3D shape as images. We can show a depth image. We can convert this as an image that show where color is coded as depth. And we can do this in different directions. It depends what works the most best for us. And we also can use color. Those. So we have 2 images. One is color, and other is depth image. And then we could analyze these 2 images with all algorithms that we learned before at image processing in OpenCV. We can find out objects and whatever. However, we could also work with point clouds, but this is a little bit more demanding. So at this point, we only, in this lecture, we only give idea how point cloud looks, how we should, the problem is already with visualization. We need some proper software tools to show point cloud, to magnify it, and what to do with point cloud. And after that, we show them, but we don't use at this lecture, let's say some point cloud library or MeshLab or some other tools that enable us some functionality for working with these point clouds. So this is working with point clouds is actually one complete lecture is only dedicated to point cloud processing. We start here with with visualization. This is already before, but with cleaning point clouds, that means how to remove noise, how to remove some background, unwanted background, how to repair these point clouds, so how to fill some holes where some data is missing or where we have some reflections and something steer out the surface, and how to clean this. Then how to smooth surfaces, how to remove some noise. Then we discuss meshing and mesh simplification. So from a lot of triangles, what we get from scanners, how to reduce number of points by some mesh simplification algorithms, what are the key parameters of this simplification, and we demonstrated this in MeshLab. So this is one software tool for, it's all again freeware, maybe you know it. And we then we show some use cases about this. When we know how to work with these point clouds, then we go to the point cloud alignment. Let's say that we do some reverse engineering application. We wish to scan objects, let's say some tool or some statue or whatever. We scan it from different viewpoints. We already know how to, what are the key important parameters. We already have meshes, we know how to clean these meshes. And then we here we learn how to merge, first of all, how to align different meshes together, and then how to, what are different algorithms for precise alignment, starting from key point to some iteration, ICTP algorithm, so on, to get a point cloud visualization of the some object of interest that we wish to reconstruct its shape. We also show them, but we don't go into detail, what to do with this point cloud then. And we have assembled, we have point cloud. This point cloud is at the end represented with points and triangles. Then we show them possibility to convert this into some NURBS surfaces, NURBS patches. Let's say we can use some software tools, let's say in SolidWorks, we can import STL of this point cloud surface mesh, and with some tools we can convert this into the NURBS patches, and based on that we can get out CAD model of the part. We only show pipeline, how to do this, but we don't go into details what are mathematics behind NURBS and so on, because this is then too much. We cannot show everything. Okay, the end, one of the last examples that we go through are sim tracking systems. So let's say that we have some robotic application where we have to weld something, and we need to follow the groove of the weld. But the problem is that when we start welding, due to the extreme heat put, these parts that we weld together can deform and the groove size can change. And we should monitor, first of all, we should find the groove, so the path of the groove, and send it to the robot controller so that the robot will always move along the groove. So why we should do this initially? Because when we clamp work pieces to some holder that hold these parts together during the welding, we have quite big variability. We cannot do same operation. We cannot repeat same thing 2 times. So we always have some differences in positioning. So if we wish to perform accurate weld, we have to measure this in advance. And for this, we use, we show them again, laser scanners, but these are more simple laser scanners with only one light plane. And we get out only profile, one profile that shows some cross section for the surface. And lastly, a robot moves this laser profiler along the groove, section it, measures center of the groove or edges of the groove, and so on, store points in memory, and after that, when we finish this, these points are sent to the robot controller, and then the robot moves precisely along this groove. But in addition to this, we have to do also corrections during the welding due to some problems with the thermal deformations and so on. So in this lecture, we actually explain them, first of all, big picture. What is the problem? What is the problem with the positioning, the tool, and so on? How to measure? So what kind of sensor we can install? This could be, or as I told you, laser scanner, what we have, or it could can be also single camera or stereo vision, whatever, depends on the object. And then how to establish communication between the measuring system and robot controller, how to extract some important parameters from the measurement, and how to then also how to calibrate. Here I have example of this, let's say for welding some big plastic pipes or plastic for source systems, some housings. Here is first of all a very nice example of this problem, because these parts are huge and we cannot repeatably position them in front of the robot. So that's the reason why we have to measure groove very well, then weld this plastic. After that, when we start welding, we also have to check on the time. We go through this case study, how to do this in practice. Yeah, so much about this in tracking. Then final lecture, a little bit what will be in the future, what are the modern trends, where everything will go in the future. And here we say a few words about smart cameras. So cameras that has already some processor in image processing capability. So camera with built-in image processing capability, so that we can already program camera not only to acquire but only to process image and give us some signal out if the workpiece is okay, if we have some misalignment, where to go, if it is misalignment, if to go to the left or to the right, or so on. Then we say about few words about modeling approaches to image processing, especially with graphic cards, GPU. So let's say some NVIDIA, CUDA, and so on. We show them what is this direction, what is FPGA, we explain them. And then we also explain them what are upcoming trends in image processing, especially in use of deep learning and convolutional neural networks. So we only, here we only show them, let's say, pipeline like this. They already know what is convolution. Then we only say, explain them what are some logic here behind. We don't go into the details because we don't have time. And we show them in practice some applications, let's say for part recognitions that work with deep learning, just to impress them what is possible today, how to recognize different parts, orientation of parts, how to train the system, and so on. So here this is more only informative, because in one lecture you cannot give a lot. It's only idea what is this and how this performs. So if you wish to be good in deep learning, you must study a little bit more than this. Yeah, so much about lectures. So yeah, maybe at this point I can say a few words about laboratory exercises. Our laboratories, I will not go into details because in this hour and a half we don't have time to go into details into the laboratory exercises. I can tell you that these laboratories exercises are very well aligned with lectures. So everything I was explaining through the lectures and structures of the lectures, the same way also laboratory exercises going in practice. So At the beginning of the semester, we start with some introduction, general instructions, case study. Then they have laboratory exercises about lightning effects, how they play with lights and different parts and observe how, in practice, how different things are visible with different configurations. Then, then they have one laboratory exercise, how to play with camera, how to connect camera to the computer, how to acquire image, how to control camera, how the image is stored into the computer. And this is done with, we show them first example in some arbitrary PC and software, RoboRealm. This is some commercial software, but it is very high-level programming, high-level application of functions and everything. Then we say a few words about Python and OpenCV, how to install. Then we actually use Raspberry Pi platforms, so each student gets its own Raspberry Pi with some small camera. And then we give them instructions how to use this Raspberry Pi, how to work with Python, a few words about Linux, and then how to start camera in Python, how to install OpenCV, how to call basic functions from of OpenCV functions in Python on Raspberry Pi, how to grab image, how to visualize image, and so on. So playing with this equipment is also an important part of these laboratory exercises. And we put also one important exercise to the camera to the lens calculation. So a little bit math and playing with these lens calculations. And then we go to the image processing. They already know how to use Raspberry Pi, this architecture. Then we go through basic image processing, starting from color conversion, thresholding, image filtering, blob detection, some calculation of blob properties, and so on. Okay, this is all about image processing. Yeah, then we also have laboratory exercise dedicated to the camera calibration. We calibrate their cameras with this chessboard. They interpret results. They have some setup with this. Yeah, then one important laboratory exercise is dedicated to the 3D shape measurement. We have 3D scanners. We have CVID1 and one scanner which I built is based on laser triangulation. And then they scan, they first of all, they use these scanners, play with them to acquire point clouds. And then they use MeshLab for working with these point clouds. So for cleaning, repairing, remeshing, stitching together different scans and so on. And at the end, each of them got its own task. And then they, with their equipment, they already have this Raspberry Pi camera. They built some application, write software to perform this task and write report. And this is then their seminar, which they present at the end of the laboratory exercises. Yeah, so maybe that's about laboratory exercises. Maybe here I can say a few words about assessment. They receive 2 grades. First is from theoretical method, from lecture. They have exam, written exam, and also oral examination. on this exam. They got some theoretical questions. They also got something to calculate, very often lenses. And this grade is half of the final grade. Then, in addition to this, they get 2 additional grades. One is from work in laboratory exercises. These include how they come prepared to the laboratory exercises, how they perform on laboratory exercises, and they also write on each laboratory exercise, they write some report. And then assistant that work that is responsible for these laboratory exercises, then grade those laboratory exercises. At the end, it provides this grade for laboratory work. And the third grade is grade for the seminar. As I told before, they got this seminar, they do some application from the scratch with this Raspberry Pi and everything. And we evaluate here how successfully student implemented this task and arrived at some solution. And also report how the student write report, how we present results, and so on. So final grade weights for final grades are here. So at the end, they get grade. We say we all are happy and say goodbye. So at this point, I'll also say goodbye and thank you. Thank you for your attention. And I open discussion.
Okay, thank you, Drago. So our first talk of the day about, again, how we do things here at the faculty. So are there any questions from the audience? So if you want, you can just either unmute yourselves or write them in chat.
Yes. Can you hear me?
Please go ahead.
Yes, there's just one question here, if it's possible. First, thank you very much for the presentation and the technique you use for teaching the students. It's really nice, and also to see how you combine it with the laboratory exercises. It is really fascinating. I just have one question, if it's possible. I saw that you used many softwares for example, the OpenCV, MATLAB, OpenCV with Python. From your experience, do you think is it maybe a little bit too much for students to have many software instead, maybe to focus just on it, to use one software? Or is it better to give them many techniques from different softwares?
Yeah, thank you very much for your nice words and question. Yeah, the primary software we use is Python. And OpenCV is actually a library for image processing that we include in Python, and the students use then OpenCV in Python for image processing. However, we also, and I would like to stress this, that this is third year of mechatronics, and our students have this from mechatronics. They also have several lectures before where they encounter not only Python, but also MATLAB, at least, or basics of C++ programming. So, those C++, MATLAB, Python, those softwares today are actually essential wherever you go, but we primarily stick to the Python. However, from time to time, we show some use case them also in, let's say, as I told you, for camera calibration, let's say in MATLAB, because there is one software tool that is very easy to use. So we don't go in detail in MATLAB, but only we show them how to use some tool which is written in MATLAB. So similar this RobRealm, which is some commercial software for image processing. This is very high level software. You need, let's say, half hour to figure out interface, and you can already build image processing pipeline and do something with this software. So we want to show them the variety of all this, because if you only stick to Python, then you always stick to programming. And you have, as you know, you have students that enjoy programming, and you have students that are afraid of programming. So we should somehow provide tools for the all categories to make them somehow that they go somehow that can manage to do these things. So if someone is not happy with programming, it is afraid of programming, we must be aware this is first cycle program. The students have 3 years and half of mechanical engineering. There are students between them that are afraid of programming. So we should provide them something that is very high level, and it's more playing with blocks and more graphical. And that's where RobRealm comes, or this camera calibration toolbox in MATLAB. It's also very high level and so on. But Python is, so you already, okay, it's not problem for our students, but it's already a little more, require a little bit more background. So we have to be somehow flexible.
Okay, now I got it. But we cannot, for example, use only, for example, MATLAB. Is it possible to use, for example, only MATLAB, since MATLAB can have all of these functions also?
Yes, definitively. MATLAB could be definitively used. You have image processing toolbox in MATLAB. You have everything in MATLAB, but this MATLAB ecosystem is super for academia, because we have academic license here, and there's no problem because MATLAB is commercial software. And then the problem is when our students get into the enterprises in practice, it's question who will buy this license. Okay, they can stick to illegal versions, but this is not how we should work, or at least how we should teach them to not to do this way. So, but Python, according to my experience, there's a lot of applications running in practice in Python. It's quite stable. OpenCV is freeware, and there's no issues on market. And I think the students, as I know your situation, your country, I think your niche is in programming. So if your students will know how to program, let's say Python, MATLAB, C++, they will quite easily get jobs on global market through freelancing and whatever. Yesterday, when I was preparing for this lecture, Rock gave me a hint to check if there is some freelancing possibilities for working in this image processing. I can say that is a lot, but you have to know programming. There is a lot of image processing. Let's say today, the first thing that fell in my eyes today is a really big development on the field of artificial intelligence and image processing and so on. And the key thing here is in databases. So people around the world collect images, or all kinds of images of problems they have, someone from some industrial application, other from people faces cars on the streets, autonomous guiding vehicles, whatever. They have databases, hundreds, thousands of images. And they need services, let's say, for image processing, for labeling images. Let's say they give you a task, okay, here I have, I don't know, 20,000 images. Go through these images and label, let's say, mark with square all red cars on those images. Let's say that they have traffic, record images of the traffic, and then they have to label all red cars, or let's say pedestrians, or whatever, so that this data is later on used by guys who develop some of these advanced neural networks for recognizing or whatever. And this is very time consuming and so on work, and they outsource this a lot. Then I also check there's plenty of what they look also for software developers for developing, let's say, software applications for some specific image processing task. Let's say you have, they send you, let's say, images of some work pieces, and then they have some setup, and then you have to develop some software, let's say in Python or C++, or I don't know what they need from the scratch to this software will perform some tasks. So I think regarding, to conclude, programming is key for success in image processing, and there is I think big opportunity on the market for earning and to get the jobs, and even to travel around and employ somewhere where it is possible.
Perfect. Thank you very much.
Thank you.
Thank you, Drago. Is there another question from the audience?
Maybe they sleep because I'm so monotonous.
No.
Maybe we should wake up them with some loud music.
That's okay. Well, it seems to me there are no further questions for you, Drago. So again, thank you all for attending. I am posting the link to evaluate the sessions after the end of the day into chat. So please save this link. We need this for the quality reporting in relation to the project. And with this, I want to thank the presenter, Professor Drago Braciun, again for the excellent lecture. And we'll continue in about half an hour with our next presenter. Thank you, Drago.
Thank you very much for listening. Have a good time in your countries, and stay well. Goodbye.
Bye.